So as we saw earlier, if t, little t, is in units of years, time measured in years, then the log of the ratio, which of course is nothing more than the return, right? The log of the ratio of st and s0 is the continuous return from time 0 to time little t. And here we're going to assume it has a mean and a variance proportional to time, and the coefficients are the ones we saw in the earlier slide. So we can, in fact, write this somewhat differently. Namely, we can say, well, because we have a normal with a mean and a variance, we can express that in terms of the standard normal. Namely, and we saw this in our earliest module, we can express that the log ratio is a constant term plus a constant term, and now we have z. Is the z, of course, is the typical, I say it right here, z is a standard normal. And this was an earlier result we saw, that if we have a normal that isn't standard, we can express it as a constant mu plus sigma times the standard normal, and that's all we've done here. And so finally, we get a way of modeling stock prices at time t. If we just generate a variety of z values from a standard normal, if we can determine a process for doing that, and we'll talk more about that in Chapter 19, but if we can generate z values and plug them into this formula, we will thereby generate a log-normally distributed sample of stock prices at time t. This is a very useful formula, both theoretically in its continuous form, where z is continuous standard normal, but also because of what it implies about simulating st values by first simulating some z values. Now, because we have the form that st, the stock price at time t, is s0 times e to a normal, we developed on an earlier slide, in particular slide 22, what the mean of that st is. And just using that prior result, namely what is the mean of a log normal variable, we derived the following formula, that the expected value of the stock price at time t, the mean, the average, the expected value of the stock price at time t, that log normally distributed stock price, its expected value is the initial stock price with a return of alpha minus delta times t. Now this may surprise you, because what this also, you can also think of this as saying, is that the return implied by this expected value is alpha minus delta times t. And that may surprise, because you may have been thinking that the return on the stock was alpha t. And instead, it's alpha minus delta t. And the answer to the apparent mystery is we cannot forget, and here it's written as a return, that the expected return is e, the expected ratio is e to the alpha minus delta times t. Now, what is the subtraction of delta t? Well, it's a recognition that the investor in the security got a return of e to the delta t in dividends, cash dividends. So this is the, in fact, this is in fact the price return, as I say here. If you have a stock that's paying continuous dividends, you can't expect the price of that stock to provide you with the return of alpha, because you're getting a return of delta in dividends. It's the total return that's alpha, and therefore the price return of the stock is alpha minus delta, and on the side you're getting cash dividends which increase that return back to the alpha. So this is a price return, and that's what we're of course assuming in our lattice, because in any model of stock prices we typically want to assume that the stock price reflects the fact that dividends have been paid to the investor. And so the return implied in that lattice or in that model should be the return explicitly reflecting the fact that some return has already been provided to the investor by way of dividends. We can then calculate the median, as this slide shows. Because we have an explicit model for the distribution of ST in terms of the distribution of standard normal Z, we saw that a couple of slides ago, the median of ST comes from the median of Z. Namely, if I just plug Z equals 0 into that earlier formula for ST, I get the median of ST. And you see what I finally get is that the median of the log normal S is smaller than its mean. Okay? So what we're saying, and it's smaller because of the adjustment of this e to the minus a half sigma squared. And again, how did I derive this formula? Just observing that the median of the S distribution comes from the median of the Z distribution, which we know is 0. So now let's revisit the connection between the log normal and the binomial models. Again, this was introduced, the idea was introduced in Chapter 11. Let's pursue it a little more detail. So we have what we now have in our log normal model is that if S is the price at time t, and S prime is the price at time t plus h. So I have an intervening period of time h, and that's the typical binomial lattice model. So I want to compare these formulas. In the binomial lattice formula or model, you go from time t to time t plus h. So what does the log normal model say about that? It says, just taking our earlier formula, S prime will be given by this simple formula where using h is the period of time and z is a standard normal variable. So in the log normal model, I can go from time t to time t plus h pricing by taking the time t price S and multiplying it by this exponentiated normal. Now, what do we do in the binomial lattice? Well, the up and down prices, which are the S prime prices, they're the prices in the next period, we have this simple formula. We take the price at the beginning of the period, and we multiply it by an up return or a down return. What is the form of the up and down return from the earlier chapters 10 and 11? They're always of the form e to some alpha times h plus or minus sigma times square root of h. So when I compare the functional form between the normally distributed assumption and the binomial model, we can see a lot that makes sense. We have a drift term which is proportional to h. In the log normal model, we have an explicit formulation of it, alpha minus delta minus a half sigma squared. And we have several formulations for what I call alpha binomial that were given in Chapter 10. And I'll review those in a minute. But then if you look at the risky term in the normal or log normal distribution, we have a sigma square root of h times a normal, standard normal z. In the binomial, we have a sigma square root of h, and in place of a standard normal z, we use a plus or minus 1. So in a sense, we're transforming we're transforming the standard normal distribution into a simple binomial distribution of plus or minus 1.